Hello, hello. All right. So I'm Ryan Friedman, and standing here with me is Rhys Mainwaring. We're going to be talking about some path planning we've done with ArduPilot. But first, we're going to talk about cross compilation. So it's very common for developers of autonomy to be writing autonomy in C++. So this is just some initial work I've done to open source a cross compiler that allows you to develop C++ applications faster when you're targeting typical ARM platforms on the drone. So basically how this works is you write software on your laptop just like you do with ArduPilot. You compile it on your laptop, but you target ARM64, and this will work for Raspberry Pi or NVIDIA Jetson. And then you can copy the binaries and runtime dependencies to the target hardware. So here's just a little hello world. I did Mav SDK as an example, which is a C++ API. To do this, we use CMake, which involves a few steps. The first is to configure, and as part of that repo is a toolchain file that sets up all the things necessary for cross-compiling. So this basically finds all the dependencies for your application and sets up all the files for the system. Now, here's the cool part. The typical way of doing this, particularly in the ROS ecosystem, is to use Docker and QEMU. But that's 10 to 20 times slower than native compilation. So if you don't have time to set up a cross compiler and you're writing big ROS applications with CI, it can cause your CI jobs to take hours, which is not really useful for rapid development. So with this step, we can now compile using the host compiler and build your targets very, very fast. So once you have those dependencies built, you can install them on the target, and here's running a hello world on the target hardware. So it's very quick, and there's obviously work to do to get it more integrated with the ROS toolchain. So I'm working on that, but at least for simple applications, feel free to go get started and file bugs if the toolchain is missing certain dependencies that you need. Any questions on that before we get into some path planning? All right, so what I've been working on with Rhys for the past couple of years with regards to path planning is sort of this high-level goal of we want to obey fences in ArduPilot, or any autopilot for that matter. We want to avoid terrain, and we also want to be able to respect max AGL constraints that are frequently required by regulations. We'd like it to work in autonomous modes, but also RTL to get home. And we want it to run on board the vehicle, so if you have a GCS failsafe, your vehicle doesn't rely on the ground station to find its way back. And we also want it to be flexible, so you can bring your own constraints. Say you want to import TFRs from your local airspace from your country, you can do that, or other kinds of constraints, you can add them. So currently with ArduPilot, plain RTL, you can't really avoid the fences. It's very easy if you have exclusions that the plane's going to fly right through them on RTL. It uses look ahead to climb over terrain. If there's a very tall, narrow mountain, you're going to climb over the mountain rather than go around it, which isn't very efficient. Copter does have a lot of algorithms that have built that work quite well. But unfortunately, these don't work on plane because plane has curvature constraints. So those constraints mean that you can pretty frequently violate your fences, especially if you're very close to them. There's a method to do breadcrumbing, but that doesn't work quite as well in plane if you use more than half your battery, unless you do some loop elimination, which takes a lot of memory. And finally, currently, the companion computers, we don't really have any libraries built up to share fences between the companion computer and fences and terrain data with the autopilot and make sure they're all synchronized. So what Rhys and I are working on is creating a tool and a framework for ArduPilot developers to build path planning. We want to make deployment easier and basically be able to deploy complex path planners, but really easy to copy it and run it on a companion computer, and support both open source planners as well as commercial solutions, and use this as a way to gather feedback and influence our design. So the first path planner that I integrated was from Shearwater.ai. They make an AI path planner called Smart Flight. Here's sort of from their product page. It uses micro weather forecasting and forecast data. It can optimize based on all these kinds of constraints. And they also support in-flight optimizations that I haven't implemented. So I'm purely doing the front planning side. So what they recently released that's in beta, I got access to it. Anyone on the dev team can get access, is this web API. So you send your request to their web API, they have a server running, it computes your path plan, and then you can execute that on the drone. So this web API is very nicely documented in a tool called Swagger. So you can see example queries, you can try the API out on the web, and then you can use it to code generate if you want to use that in like another framework that you're already doing Swagger stuff. Their planner supports 2 kinematic models, one for plane, one for copter. We want the vehicle constraints to come from the autopilot. I haven't implemented that yet. It does support keepouts with an operational area. And then when you query the planner, you can tell it what to optimize for. Currently, they support energy optimized plans, time optimized plans. So if you want to execute the mission really fast, or distance optimized plan, which is typically what most planners are doing these days. It returns the paths as well as the predicted energy usage, so you know if you'll have battery to actually do the mission, which is really nice. They're planning, like I mentioned, it's using AI to help find those routes. It's under very active development. They're a startup and they're super adaptable, so they've already made some changes to the API to support Autopilot. And this API makes it really easy to integrate with your own custom GCS if you're not using what I've developed. So to start, the easiest path forward for me to get this working with Autopilot was with Mav Proxy. I wrote a module that authenticates with their server based on a bearer token. You can configure the start and the goal and the vehicle constraints. We can send fences, and then you get back a path. And then we convert that for waypoints for an auto mission. There's the pull request. And if you want to try this out, you just need an API key, which I can help you get one. So using the plugin, here's an example with a plane where we fly across a larger area where you actually want to take advantage of these energy optimizations. So as a paragliding pilot myself, I know that it's pretty advantageous during the day to fly along the tops of mountains because that's where the thermals are. So you can see here, this green path is the energy optimized route. They're taking advantage of both the local wind gradients as well as predicted thermals. And if you took this path, you'd expect to consume less battery and end up having more battery for other maneuvers at the end. So to test this, I like to use CITL. I've also refreshed Mavcesium this last year. So anyone can use Mavcesium. You just use module load cesium in Mav Proxy, and you now have a 3D view with a HUD, which is handy for flying really far away, or just testing in CITL with terrain. So that's now working with the planner, and you can see us executing a route right there. So for the demo, I just did something simple where I tried to create a plan to avoid the tree. You can see here with the geofence setup, there's the energy optimized route and the distance optimized route go different ways, and that's because of the wind coming from the south. It's more advantageous to go one way than the other. I did have to play around because this is quite a small area. Obviously, with a small area, the energy optimization is going to not really be that different, but it's just an example of on a smaller scale. So some of the limitations right now are the fences aren't synced between Map Proxy and the planner, so I'm just manually hard coding those just for the purpose of this demo, so that's just something to implement. It does require your GCS or your drone to have an internet to call their planning service, but they do support self-hosting that planner if you want to do that. And the vehicle parameters are obviously also not automatically pulled from the autopilot, so we don't know like climb rate constraints or turn radius constraints quite yet. So as far as the demo earlier, what you saw was the quadcopter taking off to go execute a plan that I generated around the tree. And so what happened was, so I uploaded the path to the copter, turned on auto. Along the way there, I lost telemetry. We thought it was a GCS failsafe. We disabled that. We tried again. And then basically when it happened again, same thing, we lost telemetry. Autopilot was continuing the mission. It tried to send a fence speech message, but I didn't get that because I didn't have a link. The vehicle turned around, ended up in RTL. And the reason for this was basically an inclusion or a keep-in fence around the home location that I didn't know I had set up on the copter from a while ago. So that wasn't displayed. And then autopilot basically recognized this condition, came back home safely, but we couldn't follow the plan because it was outside the fence. So autopilot did what it was supposed to do and just missed something in some configuration. And then here's just the parameters I had for the demo. So if I would have looked at the parameters, I would have seen that. But this is the nature of doing a demo for the first time. I wanted to keep it exciting, and unfortunately didn't get to fly the route, but I at least know the waypoints weren't way up in the sky or below the earth. So it looked like it was doing the right thing with regards to terrain, flying nice and low. So I'm at 9 minutes. I think I'll skip the demo for now on Siddle, and I'll let Rhys talk about some of his work. And then if we have time, we'll come back to that.
Got slides for that, Ryan?
Yep.
Okay. So, some background on the demonstration we tried to run earlier and didn't quite manage. So a lot of our work is based off a planner that has been put together by JLIM and various teams at ETHZ. And this is for like dealing with path planning in very steep terrain. And they've written a really nice ROS package for that. We help port it to ROS 2, so that's all available online. But when using this, they currently use tools like RViz as a ground control station, and it's not very easy to integrate with ArduPilot and our terrain data that we have on integrated with our autopilots and tools like MapProxy. So what it's very powerful. It uses the underlying paths that use a Dubbins curve. So it assumes that there's a safe place to start. You can find a loiter to start, and you can find a loiter to end. And then given those two constraints, it will see if it can find a feasible path, honoring various climb rate limitations for the plane, but also making sure that it stays within altitude bounds and satisfies kind of the terrain constraints. The public version doesn't include fences. I believe that there's a sort of like private repositories which do, but we don't have access. So that was the inspiration for our work. It's a very nice piece of work. It's documented. There's papers and details there. So we wanted to try and simplify that and see whether we could get something working integrated with ArduPilot for experimenting on, and reduce the overhead of integrating. So we've ported the core planner to Python. So that's very slow, but it actually sits over the top of a very fast library, which is the OMPL library. This is a motion planning library for state space planning. It's used in industrial robotics. So if any of you are familiar with the ROS MoveIt packages, OMPL is the underlying planning library that's used to plan kinematic paths for robotic arms. So they avoid collisions and they get to start and end points. So it can be used with different state spaces, and the one that we're using it is this Dubbins airplane state space. The library here, Terrain NavPy, is the Python port of the ETHZ path planner. So the entire state space is written in Python, which means it's quite expensive and slow to calculate. But more recently, some of those state spaces have been implemented in C++. So there's a much faster version that we can run of this, but it's not currently integrated with our work. So it's a slow planner, but what's good about it, because it's Python, it's really easy to integrate additional constraints. So it was quite straightforward just to pull the fence inclusion and exclusion fences from MapProxy and update the validator for the states to make sure that we could include that as well as terrain. And that makes it easy to deploy. It means it's easier to get across different platforms and things as well. So dependencies, MapProxy's Python, you can write tests around it. So I've got a full test suite for the terrain planner in Python. And OMPL supply the binaries for a reasonable number of targets and against about 3 different versions of Python. So it's much easier to share and get this thing running on a variety of machines. So, as mentioned earlier, the planner obeys curvature constraints, so you can set a loiter radius effectively, or a turn radius for the aircraft, climb rates. And the overall idea is that we're going to, it's a MAV proxy module for integrating the planner into MAV proxy. It's got two modes. It can either run as part of the ground control station, or it can run in a headless mode on the onboard computer. The planner itself runs in a separate process so that it doesn't stop the MAV proxy loop while it's looking for a solution, and doesn't kind of compete with resources on the same thread. So it's a core library that can be integrated with other systems as well. So not specifically MAV proxy. So there's an API for that. So here's an example where we do have terrain, and so the general structure of these things is it's straight lines with curves, and there's a constant climb rate along either the curves or the straight lines. If you can't hit a state going from one point to another, the model will spiral upwards. So you've got kind of curves, or you're spiraling, or you're going in straight lines. And that's, so any path you'll see created by a Dublin style planner will have that structure. It's a random sampling planner, and the way that OMPL works, it tries a different state sampler each time. So you're not going to, if you rerun the planner, you'll get a different route. And that can be useful if it can't find a solution the first time. I think one of the things about figuring out how to initialize it well, so that if you want to force reproducible results, would be useful. It does have a facility in it, but we don't have that shown at the moment. So then I'm going to just switch computers over now, and hopefully this comes up. Is it showing up on the screen? Yeah, okay, great. So it may have been a little bit hard to follow what we were trying to do this morning with the plane, because we don't have obvious terrain to fly around. We had to create some obstacles for the planner to work with. So here we've gone to town on putting lots and lots of extra obstacles in the way of getting from our start goal to our end goal. So the planner allows you to set a start, and then it sets a goal. And if you try and set the goal somewhere it shouldn't be, the planner's not going to like it. So the goal has to be valid for the planner to accept it, in that it has to satisfy both fence requirements and terrain. So the terrain here is pretty easy because it's all flat, but quite often with tricky terrain, finding a flat spot to loiter in will be difficult. Now, what we haven't done in the library so far, which is the hard problem, is when the plane fail-safes, it needs to find a safe place to loiter, and we would like to be able to do that on board. So the first thing that happens is the plane fail-safes. It goes into a planned return to land, and it needs to find a place to circle while it computes the return path. Now that has to look ahead in some sense, and that it's currently an unsolved problem for us. And ideally, it would be done on board rather than on a companion computer. So it parks the plane up somewhere that it can cycle around while a good solution is hunted for. Now, with the C++ versions of the planner, that should be computed within a loiter cycle. Because we're running on Python, it is not going to do that. So then on the ground control station, we can use this for planning as well. So it's not just for, so if we say, can you find us a mission that will route around all these obstacles? So here the planner is going to start looking, and it comes up because it's a sample-based planner. It'll come up with a valid solution, which it'll lock in, and then it'll start looking for a better one. So you give the planner a time budget, and you say, I'm going to say allocate maybe 20 seconds to find a solution. So here we've got a solution that wiggles around all the different exclusion circles and gets us from our start to finish. Now, the next thing, the ETH planner is designed to be used with an off-board controller, so a path guidance controller. We have a PR for one of those, which is I haven't finished to do all the tests for. But in that case, the companion computer has the path and it knows the accelerations and the velocities that it needs to drive around, and it runs for that. So what we've done instead is get the planner to generate the waypoints, Here it's just done as a series of breadcrumbs. Another way of generating them is to link these with loiters and straight lines, and it's a much more natural path for the plane to follow. But there's some glitches in how it may cycle round and take you into an exclusion fence if we do that. So we then accept the mission and we set the plane off following the path. And off it goes. Now this is running, so the setup here, this is running Simon hardware. So this is exactly the same setup, apart from versions of the flight controller, that would be running in the plane. So the Simon hardware support in ArduPilot is really nice. It means you can flash your flight controller, but it'll have the CITL running on it, and then it's integrated with the Pi, so all the connectivity is all the same. And the idea this morning was just to have this working, which it was, and then basically drop the Pi into the plane and just swap the plugs over. But unfortunately, the board has had a kind of a change of pinouts on the way through. We managed to choose the one UART, which had been moved out of all the other free ones, which is a bit unfortunate. So as we move, I'm going to wait for, because it's Simon hardware, I don't think the speed up works. Are we out of time?
Pretty much, yeah.
Yeah, okay. Okay. Okay.
Questions? Okay, thank you very much, both. A round of applause.
Thank you for joining us for the ArduPilot Developers Conference 2025. With thanks to our sponsors, 3DXR, Aerosystems West, CUAV, QPilot, High-Tech, Polybro, IR-Lock, KH Unmanned, Kraus Hamdani Aerospace, Maytech, Modal AI, Northwest Blue, SD Model, and Theseus. Organised by KH Unmanned. Hosted by 3DXR in North Yorkshire. Broadcast by Q Branch.